Okay, so in our previous segment, we found out that when you start smashing things like protons together, you end up with a plethora of other fundamental particles that come out. And the goal was to actually simplify nature. And so we've got all of these different particles, and things are getting more and more complicated. Well, in 1964, there were two scientists by the name of Gell-Mann and Zellwig, and they proposed that all of these new particles were composed of quarks. And then you also needed to have these things called leptons in order to make the reactions work. So let's first concentrate on what the quarks are, and then we'll talk about what the leptons are. So you can explain all of these particles by using just 6 kinds of quarks. So you have the up quark and the down quark, the charmed quark and the strange quark, the top quark and the bottom quark. Now you might be wondering, where did all these names come from? Well, one of the scientists liked to read Alice Through the Looking Glass. And so there's a poem in that book that uses those words. And so he just adopted those words as being the names of these fundamental particles. So ordinary matter, such as protons and neutrons, are going to be composed of the up and the down quarks. So you see there that there's a picture of a proton. Okay, now a proton has positive charge, and then next to it is a neutron. And a neutron is going to have neutral charge. So it's not going to have any electrical charge to it. So they propose that inside the proton is going to be 3 quarks. Okay, and the quarks are going to be an up quark and an up quark and then a down quark. And then the neutron is going to be a up quark and then a down quark and then a down quark. So notice that the two particles are identical to each other, except that this one over here has an up quark and then this one over here has a down quark. But other than that, the two particles are identical. Then another thing that they showed was that the quarks had a fraction of an electrical charge. And so it turned out that the up quark had a charge of 2/3, positive 2/3, and then the down quark had a charge of negative 1/3. So this is highly unusual, but you've got to have partial charges in order to create these things. So let's take an up and a down. So an up would be 2/3 plus 2/3 plus a negative 1/3. So 2 plus 2 makes 4. 4 minus 1 is 3. 3 divided by 3 is 1. So that this thing would have an overall charge of plus 1, which it does. Let's try it for the neutron. So with the neutron, we're going to have a 2/3 plus a negative 1/3 plus a negative 1/3. So negative 1 and negative 1 makes negative 2. Negative 2 and positive 2 makes 0. 0 divided by 3 is 0. So that this thing would have an overall charge of 0, which the neutron does. So that if we go back to this chart here, the nucleons, such as the protons and the neutrons, are composed of 3 quarks. What about the mesons? What are the mesons composed of? Well, we said that mesons are lighter than nucleons, and it turns out that they are composed of 2 quarks. And one of the quarks is going to be matter, and then the other quark turns out to be antimatter. It's anti-particle. So that in addition to having an up quark, you could have a anti-up quark, and we put a bar over the top of it, and so that means it's the antimatter particle that goes with an up quark. And you could have a down quark, and its antimatter particle would be this one. So you put a bar over the top of it. So if you combine a quark and an antiquark together, that's where the mesons come from. And then what about the hyperons? So what were the hyperons? Well, they were composed of more than 3 quarks. So you can have larger particles that are composed of 5 quarks, and you can have other particles that are composed of 7 quarks, and then theoretically you could have even larger particles than that. But that's what the hyperons turned out to be. So everything is being explained in terms of these quark things. So the next question is, well, why do we need to have even more particles? So why do we need to have leptons? Okay, we're going to eventually talk about the weak nuclear force. And so if you recall, when we talked about the weak nuclear force, it could change a proton into a neutron, or it could change a neutron into a proton. So that's what the weak nuclear force could do. So if you wanted to change a proton into a neutron, what would you have to do? You would have to change this one right here. So this up quark has to change into a down quark. And in the process of doing that, leptons are going to be emitted. So that there are 2 leptons that go with the up and the down quarks. And so they are called the electron. That should sound familiar. So that's the ordinary electron that makes up the cloud of the atom. And then you also have a thing called a neutrino is given off. And so those are the 2 leptons that go with the up and the down. Then with the charm and the strange quarks, they have their own set of leptons called a muon, and also the neutrino that goes with the muon. Okay, and then you also have the tau neutrino lepton, and then also a neutrino that goes with the tau particle, and they are the 2 leptons that go with the top and the bottom quarks. So it's still not very good, because we would really like to have just one particle that could make any other particle in the universe. And so now we need to have 12 in order to be able to do it. But it was a major breakthrough in 1964 when they came up with the quark idea. So there is a little video here that I would like for you to watch, and it's called IB Physics, Quarks, Leptons, and Antiparticles. So go ahead and watch that on YouTube before we go on to our next slide. Okay? All right. So let's take a break, and when we come back, we will discuss what matter and antimatter are.